Hey, how's it going? Good to have you back. Today we have a super duper awesome special guest. Please welcome the world famous, the one and only, world renowned, boy, I say like the world famous one and only a lot, so let me think of a different way to introduce him. My guest today is a world renowned storyteller. Why is he teaching statistics? Oh, you'll see. Please welcome Mr. William Richards.
Thank you all for giving me the opportunity to be here today. That reminds me when I was a boy and I had the opportunity to...
Actually, we have a lot of content to cover today, so stick to the script, brother.
Then why am I here?
Moving along. Logistic regression. So here are the objectives today. Understand when to use logistic regression. Understand a logistic regression's best fitting line, the assumptions of logistic, uses of logistic, using Flexplot to visualize logistic regressions, both at the bivariate and the multivariate level, as well as Ghostlines. Ghostlines are awesome. Estimates of interest for logistic regression, such as odds ratios, standardized odds ratios, predicted probabilities, etc. Weaknesses of logistic regression, and how to do model comparisons within logistic, and the metrics of interest for model comparisons. But first, let's begin with the table saw data set. And now it is time for our friend, William Richards, I think was his name. And I don't remember what he sounds like. We'll just make something up. So, Mr. Richards, this is what you do best. So we have the table saw data set, and what this is this, I'll get to Mr. Richards here in a minute. So what the table saw data set is it contains 1,387 observations of woodworkers, and during a 1-hour observation period, each was scored by 3 raters on safety and attention. And each worker was also asked if they had ever had a table saw injury. By the way, this is completely fabricated data, but as one who has been injured by a table saw, twice, no less, this is something that's of interest. Oh, you want to see my scar? Let's see. That's a nasty little thumb there. And notice my left thumb, which for you looks like the right, is about 1/4 inch shorter than my other one. You want to know why? Because I cut the thing off with the table saw. Let's go with Mr. Richards to tell this story. Now, are you okay with pretending that it was you that had this injury? Of course. When I was in the workshop 2 years ago, I was cutting a piece of wood. And you see, one of the safety procedures with cutting wood is that you only have the blade about that high above the workpiece. But I had a dull blade, first mistake. And the higher you have the blade, the faster and less bogged down the saw gets when it tries to cut a piece of wood. Again, first mistake. I had it way too far up. Second mistake, as I was pushing the wood through, I took my push sticks and I put them aside. Second big mistake. And then there was a little piece of wood dangling at the edge of the table saw. And here comes my third and most final and most dubious of mistakes. I reached across the table saw to knock that piece of wood onto the floor. And having been used to the table saw blade being that high, not that high, I reached across and my thumb intersected with the blade and cut off 1/4 inch of my thumb. A surgery later, and 2 years, I still have no feeling in my thumb. So is this a topic, ladies and gentlemen, I ask of you, that is of interest to me? Is it of interest to you? Probably not. But it makes a cool data set. Wow, that was a captivating story. Thank you, Mr. Richards. So with that, we have 4 variables that were measured: safety score, attention score, the gender of the woodworker, and whether they self-reported on having an injury or not. So when do we use logistic regression? We use logistic regression when the outcome is binary. Well, you can't fit a straight line to binary data, can you? So we got disease and no disease, for example, dead versus not dead, male versus female, car accident versus no car accident, inpatient, oh, like an inpatient clinic, were they an inpatient versus not? Or in this case, were they injured by a table saw in their career or in their lifetime or not? So, one question to ask, is it a good idea to dichotomize a continuous variable just to use logistic regression? No! Is it a good idea to dichotomize an independent variable just to make the analysis easier? No! Bad idea. Because you are throwing away information. All you're doing is increasing unreliability, and you're going to screw things up that way. So don't ever dichotomize people into like depressed versus not, or happy versus not, or stressed versus not. If it's a continuous measure, leave it a continuous measure. That's always the best way to deal with it. So what can you use logistic regression for? You can use it for classification. For example, you can take a bunch of predictors and try to figure out who's going to develop diabetes. Or you could have a bunch of indicators and say, will this person end up in prison? Or you could use it for classification. So why do some people engage in NSSI, which is non-suicidal self-injury, and others do not? Why do some men sexually assault women and others do not? Why do some smoke and others do not? Why do some cut off their thumbs and others do not? I don't know. That's why I got this data set. I'm using statistics to keep the remaining digits. So visualizing regression, and what the freak is it doing anyway? So here's an example of what we call an ogive function. I know it's kind of a funny name, but that's the term that you use to describe the shape of it. And so what logistic regression is doing is it's got binary responses, either a yes or a 1 in the plot here, or a no, which is a 0. And it's got a bunch of data points, and what it's trying to do is it's trying to fit a line that we say asymptotes at the top and at the bottom, meaning that it goes straight and then eventually it levels out, because you can't get more than 1. The response is either 0 or 1, so it's got to map a function like that. And so how do you read this? Well, like that text says there, with a score of 74 on the continuous variable, if you go up, it says about 50% of the people have the disease, or whatever the binary factor is. And likewise, with a score of 65 down here, almost nobody has the disease, so it is predicting that nobody has the disease. And basically what logistic regression is doing is just trying to find the best fitting bendy curvy line thingy of a jigger. So that makes them a little bit awkward to visualize, but it's still possible. So now let's look at how a regression function might look with real fake data, because I simulated this data. Well, actually, let me go back here. Notice how pretty that is. Now in the middle here, there is very little overlap between data points. There are, let's see, 1, 2, 3, 4 that overlap with about 4 data points here. And so that would be ideal if those, so if your measure, if those low on the measure, none of them had a 1, and those high on the measure, none of them had a 0, and very little overlap, that would be ideal. That would be awesome if logistic regression worked that way, but unfortunately it doesn't. Usually it looks a little more like this. So over here you can see I've jittered the 1s of table saw injury and the 0s of table saw injury, and there's a whole lot of overlap going on here. And so that's usually what happens with logistic regression, is that you're going to get a lot more overlap than that. So fortunately, when we're trying to visualize logistic regression, Flexplot has absolutely no issues with visualizing logistic regression. It just knows implicitly to make this kind of plot. My goodness, my dog is driving me bonkers. One moment, please. And we are back, ladies and gentlemen. My deepest and sincerest apologies, and my guest has left because I can't remember what he sounds like. And I wasn't liking him anyway. Okay, so same as before, we can use Flexplot. All is good. The only difference here is that we need to say method equals logistic, and it will tell R to fit a logistic shape. Otherwise, it's going to try to fit a lowest line, and it's going to look kind of funky. The other thing is I've modified, since my last video, the jitter function. It used to be that you would say jitter equals true or jitter equals false. And now what you can do is you can specify how much to jitter X and how much to jitter Y. And so in this case, I'm jittering X by 0.5 and Y by 0.01. So that's a handy little argument to use. And so what this says is the more safe you are, the lower the probability of injury. So again, on the y-axis here is probability of injury. Notice that it goes down as safety goes up, which you would hope that's the case. But we can also visualize multivariate relations. Wahoo! So here are 3 examples using the Flexplot function. So in the first one, we are looking at safety and gender. And again, using method equals logistic, and the alpha and the jitter and the method are all going to be the same across these. The only thing that's changing is the formula. So in the bottom left image, we have males versus females. So females in general have a lower probability of being injured than males do. And you can see that just by the fact that the red line is lower on the y-axis than the other one, although they kind of intersect once you get to. So basically what this is saying is that if you become unsafe enough, that males and females score about the same. And then over here we've got looking at the relationship between injury and safety, conditional on attention. And that's actually kind of hard to compare across columns, but I'll give you the Ghostline tool, folks, which will make it a lot easier here in a minute. And so I guess what we could do is we could kind of compare the top across here. Again, it's a little hard, so it seems to be that as attention increases, the injury probability goes down slightly for a given safety value. And then we can do a super multivariate plot where we look at injury as a function of safety, attention, and gender. Holy cow, we got 3 variables in there. And across all panels, the females tend to have a lower probability of injury, and as safety score increases, injury goes down. And it's kind of hard to see what attention is doing, but I think in the next plot we're going to see that a little bit better. Not yet. Okay, so now we're going to talk about Ghostlines. The problem with these sorts of plots here is that it's really hard to visualize, it's hard to compare lines across panels. That's where Ghostlines come in. So the idea is that the further our eye has to travel, the more difficult it is to compare the predictions of 2 lines, and that's where a ghost line comes in. So a ghost line shows the relationship between X and Y in one panel, but it's repeated in the other panel, so it's easier to compare. So it's kind of like a ghost car in a video game. I can't remember which of my students, I mentioned this, what do you call it, this ghost line idea for plotting, and somebody said, oh, like the video game, blah, 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 blah. Can't remember who that was. I would totally give you props here, but sorry, can't remember who that was. So props your way, whoever you are. So it's kind of like a ghost car where they have this kind of transparent car in a video game race that shows how, I don't know, your last performance was, or shows what you were doing when you got the record or whatever it is. So it's kind of that similar idea that it shows a line of a particular area but repeated across panels. So for a visual, here's an example. So what I am doing in this top bit of code, so the formula is going to be the same. Safety given, remember, whatever is put first is put on the x-axis. First one after pipe is going to be binned and put in the column panels, and then the second one binned is going to be in the row panels. And what we are now telling it is we're going to say make the ghost line gray, and what we are telling it is we are saying, all right, reference off of somebody who has an attention of 25 and their gender is male. And so what the function is going to do is it's going to find the appropriate bin. So in this case, it would be in this one because this value of 25 falls between 22 and 30. and then it's going to find the male line, and so you'll notice that the ghost line intersects exactly with that panel. And so the ghost reference, we're basically saying compare everybody else to a male who has an attention score between 22 and 30. And so you'll notice that that line is repeated across all the panels, which makes it a whole lot easier to compare it. And I got to give props to Victor on that one, not because he came up with the idea, but he basically came to me one day and he said, hey, I don't even know if this was his question, but this is my memory of the question. He said, hey, how do you visualize a multiple logistic regression? And I said, that's a dang good question. I have no idea. And I started thinking, I wonder if you could like put this line that's repeated across all of them. And so that's where the idea of ghost lines came in. So thanks, Victor. You are the man. All right. So what does this tell us? It tells us that all the female panels generally predict lower rates of injury. So the blue lines, which are the female lines, or I'm sorry, up above here, in the top panel, those are the females, and in every situation, just about always across the range of safety and attention, females are scoring lower than males. Cool. Another thing that we could look at is as attention increases, one is less likely to get injured, and so that makes it a lot easier to see with the ghost line now. So you'll notice that at low levels, the lines, at least for the males, are basically the same, but as you increase, notice how the blue line gets progressively a little bit smaller. So these blue lines here are saying that those with the higher attention scores tend to have lower probabilities of getting injured, which is kind of cool. And of course, as safety increases, injury decreases, which we've seen throughout all the panels. And by the way, like this note says right here, this will fail. I'm saying injury tilde safety plus gender. So one of the unfortunate consequences of having a ghost line is you can't put a factor, you can't put a second thing before the pipe. Here, the vertical pipe. So we got safety plus gender. That will fail because we have plus gender. And the reason why that'll fail is because normally when you put safety plus gender there, gender is going to show up as two separate lines. But we're adding a ghost line, so it's actually going to make three separate lines. So it would just be confusing. So I just said, you know what? If we're ever doing a ghost line, you can't have a second variable before the vertical pipe. Make sense? And so instead, you got to put it on the right side of it. So that will give you problems if you try it. And so now, as I've said in the past, and as I will say repeatedly, anytime there is more than one option to plot a graphic, by golly, we better plot multiple ways then. And so before we put safety on the x-axis, now we're going to put attention on the x-axis and put safety in the bins. And what this tells us is there is more uncertainty here. Notice that most of the lines, regardless of what color and what panel it is, they don't go as high and as low. And so what that tells you with a logistic regression is that it is predicting a lot more people are going to be in the 50% probability area, rather than it's just much less certain than it was before. In other words, attention is less predictive than safety. So notice what we did, y'all. We just visualized before we modeled anything. And I haven't, as I've been teaching you guys through these videos, I haven't been as good as I ought to have been about following the 8 steps data analysis. Well, I'm going to change that. Now with logistic regression, it's actually not strictly necessary to visualize things. Well, I'd say it's still necessary, but it's not as necessary as it was before, because logistic regression actually doesn't make any assumptions, which we'll talk about again here in a minute. But it does help us catch errors with our data. And the pictures are pretty. So for example, if we were looking at this plot and we noticed that as safety increased, injury also increased, we'd say, what the heck? That's not supposed to happen. The more safe you are, the more likely you're going to get an injury. That would be weird. And so being able to visualize it gives us a chance to say, hey, wait a minute. Because sometimes the conversion from a factor to a number might flip things and that sort of thing. And that's actually kind of common in logistic regression. You might think, oh shoot, I thought 1 would be injured, when in reality, in the background, the computer's thinking 0, or not injured is the 1. Anyway, you get the idea. So estimates of interest. So far we've talked about how to visualize logistic regression. Now we're going to go into looking at what the numbers actually mean. Because remember, visuals are great, numbers are great, but either of them alone suck. So we got to put them together. So now we'll talk about the estimates, and to do that we need to introduce a little bit of math. So with that, here are the mathematical equations, and those are scary. Like, even me, I'm like terrified right now. No, not really, but kind of scary looking, especially since you got all these exponents. So this right here shows the probability of getting injured for a particular x. So if you want to compute somebody's probability of getting injured, it is equal to the natural exponent raised to the a. In this case, instead of using b0, I'm using a. Why? Because I'm lazy and I copied this from online. Anyway, that's the intercept. That's the slope right there. And so e to the whatever divided by 1 plus e to the whatever. And if we were to solve for a plus bx, what we would get is the natural log of the probability divided by 1 minus the probability is equal to alpha plus beta times x. And so, by the way, this right here is the odds. And so, yeah, does that look familiar? We've got an intercept plus a slope times a variable. Holy cow, we've seen that before, haven't we? Left side don't look familiar, but the right side certainly looks familiar. And so what have we done? We have regressionified the binary response. And what we do is we call this the generalized linear model. And that is when we convert something tricky, such as this up here, into something familiar, into something linear. Now you know where generalized linear model comes from. What we are doing is we are turning something crazy into something linear so that it's something that we could understand and use. Some of the, basically, we're just using the exact same regression theory we've always used, but on a function of the variables, if that makes sense. So except now what has happened is our y has been converted from a 1 and a 0 to the log of the odds. So now the estimates are kind of meaningless. In other words, when you see a slope and an intercept, it tells you what happens on the scale of the log odds, which isn't very intuitive. So here's an example. We would like some hardcore numbers to tell us what our model found, but logistic regression's can't say it. This is YouTube. And anyway. Logistic regression is a bit tricky. So the coefficients aren't terribly intuitive. So if we were to run the model glm.mod.full, injury tilde safety plus attention plus gender. And by the way, that's the code for doing logistic regression is instead of LM, which we did previously, we do GLM for generalized linear model. And then the other thing we have to specify is family equals binomial. And next week, I think, if we have time, I will talk about different families we could use, because we could use a Poisson, we could use a negative binomial, we could use a gamma, etc., etc., etc. So anyway, that's how you run the logistic regression code. And then if you were to do summary, glm.mod.full, it will give you a familiar looking table like this. Don't worry about the call, that just tells you what formula you ran. The deviance, residuals, just gives you the residuals. And now it gives you coefficients with an estimate, standard error, a z-value, and oh no, did I cut off the p-values? Uh-oh! My mistake, intentional mistake. So anyway, these estimates are not very helpful because they are on the log odds scale. So what that tells you is that for the male, so the females are the referent group here. So that right there is the log of the odds for females. And this is the change in log odds for those who are male. And likewise, as you increase in 1 unit on safety, your log of the odds of getting injured decreases by 0.36. Oh, look at that. For every unit increase in safety. Oh, yeah, that's kind of what I said. So fight for to the rescue. Woo! So remember the estimates function that we used back in univariate, and I think we might have used it here in the multivariate class. Well, fortunately for you, it took me a long time, so y'all better be thankful. Y'all. I created a estimates function that works for GLMs. So if you were to take the estimates function and then supply as an argument the glm.mod.full, it's going to give you a lot of estimates that are a little more informative than the raw coefficients. So of course I state the raw coefficients. Those are the same as before. Wahoo, yay. And now what we also got is we've got the odds ratio and the inverse odds ratio. And for the intercept here, which is the females, it actually doesn't make sense to talk about that, but these other ones do make a little more sense. And so for example, the inverse odds ratio, because as you guys know, when we talked about the, the BIC, sometimes I like to invert it because I can understand numbers greater than 1 easier than I can understand numbers less than 1. So what this tells you is as you increase in safety by a point, or for every increase in safety, the odds of getting injured relative to somebody who stayed at the same level of safety increases by 1.4. Boy, that was a mouthful to say, but it's actually necessary because that's exactly what an odds ratio means. And we'll get more into what an odds ratio means and may not be the most intuitive metric here in a minute. But here's the thing. These have different scales. And so a 1 unit increase may be small relative to the scale of the measure. So if you've got a scale that goes from like 1 to 100, a 1 unit increase is 1/100th of the range of the scale. Whereas if you've got a scale that goes from 1 to 5, a 1 unit increase is 20% of the scale. And so to try to compare odds ratios between two scales that don't have the same metric is kind of not a good idea, if that makes sense. So in a situation like that, that's where it's good to have these standardized odds ratios. And so that makes it a little bit more intuitive to interpret. So this number right here, this 2.08 for safety, says for every standard deviation increase in safety, the odds of having an injury relative to someone who stays at the safety value My head is already exploding. How about yours? So remember what an odds is. It is the probability of something happening divided by the probability of it not happening. So what are your odds of getting a 2 when you roll the dice? Well, that's going to be the probability of getting a 2, which is 1/6, divided by the probability of not getting it, so 5/6. So that's what an odds is. So in this case, it's the probability of injury divided by the probability of not getting injured. So if the odds is 2, I am twice as likely to get injured as to not get injured. Simple enough? Okay, that's intuitive so far. But then we're talking about odds ratios. So we've got an odds ratio here. So for example, one odds ratio might be the probability of injury given that you're male divided by the probability of no injury given that you're male, divided by the probability of injury given that you're female, divided by the probability of no injury given that you're female. So that's a lot of ratios going on there. So I'd say it's time for a more intuitive metric. And what is more intuitive than probabilities? Like, I can understand probabilities. Hey, what happens when I go from this to this? Well, my probability increases by 0.25. So I increase my probability by 25%. Well, that's intuitive. So with that, again, Pfeiffer to the rescue. That's what the final column shows. It is the difference in prediction for those at +1 versus -1 standard deviations on the predictor, if that makes sense, at least for numeric predictors. So right here, this 0.34 for safety, that says that somebody who has a safety score one standard deviation above the mean has a 34% lower probability of getting injured relative to someone who is one standard deviation below the mean of safety. And likewise for attention, somebody who is one standard deviation above on attention is 13% less likely than somebody who is one standard deviation below on attention. So this tells us that safety is more predictive than attention is, because the differences in predictions are much greater. So like I said, that's what that does for numeric predictors, but for categorical predictors, it just shows the differences between categories. So in this first column, it shows you the probability of a female getting injured for our particular data set of woodworkers, averaged across all safety and all attention, that sort of thing. So females have a 40% chance of getting injured, and males have a 15% chance greater than females, if that makes sense. So to add those up, males have a 55% chance of getting injured, whereas females only have a 40% chance of getting injured for a difference of 15%. Make sense? Oh, and look at that. I made like arrows and stuff. So anyway, now you can also do more detailed predictions. By the way, y'all owe me big time. I'm just saying, it took me like 8 hours to write all these functions in logistic regression, so the least I deserve is a high five when I get to class or something like that. And for those of you who don't go to class, then hey, yeah, this is a YouTube channel. You can give me a thumbs up. Dagnabbit. Okay, so for more detailed predictions, what we can use is the anchor.predictions function, and it takes two arguments. It takes the model that we fit, and it takes a vector, or it doesn't even have to be a vector. Anyway, we just tell it, in quotes, what variable we want to generate predictions for. So in this first one, it says, just give me predictions for attention. And so what that will show you is it shows you the prediction for somebody who is +1 standard deviation on attention and -1 standard deviation on attention, and it shows you their predicted probability of getting a table saw injury. And also it gives you a note. So remember, the model had safety, gender, and attention. And so this note basically says, hey, you didn't specify anything for safety and gender. I'm going to predict the average for quantitative variables and take the first level of categorical variables. So basically this would be this 33% is the prediction for someone who is one standard deviation above on attention, but average on safety, and I believe female is, yeah, and then this is for female. So it just randomly chooses whichever category it wants to, kind of, sort of. And so it's going to choose females. So this is females who are average on safety, but +1 standard deviation on attention, versus females who are average in safety and -1 on attention. So anyway, here's another line, and there's this argument called shut up, or you can tell the computer to shut up. All right, I don't need your warnings. So that's what that says, is don't give me that warning anymore. I get it. And that will produce a table that shows you the different predicted values for different combinations of attention and gender. And looks like the lowest here is males who are 1 standard deviation below on attention. They have a 62-ish% chance of getting an injury, relative to females, for example, who are 1 standard deviation above on attention. They have a 33% chance. This is a whole lot more intuitive, isn't it? This whole log odds and that sort of thing, that's kind of confusing. But this, I can do this. And then finally we got safety and gender and the predictions there. So you could always do that with your model. Just specify what variables you want to predict, and it's going to predict those for you. So let's step back, big picture. We talked about visualizing logistic regression. We can use a Flexplot function. We could use Ghostlines in there. By the way, you could use Ghostlines for multiple regression too, which is kind of cool. Although I haven't really tested that yet, so it should work. Anyway, so we've talked about visualizing things in Ghostlines. We've talked about the estimates of interest, where we can look at the raw estimates, which are on the log odds scale, which aren't very intuitive. We could convert them to odds ratios, and we could do standardized odds ratios, but even then, still not very informative. So then we talked about just doing anchored predictions, where we'd look at somebody one standard deviation above, one standard deviation below the mean, and looking at the differences in predictions. And now we are getting into model comparisons in logistic regression. So weaknesses of logistic regression, they have the same weaknesses as linear regression. So very sensitive to overfitting. How do you combat this? And it's very sensitive to order of entry. How do you combat this? It's very sensitive to multicollinearity and who gets credit. And how do you combat this? Well, as you remember before, we overcame these weaknesses by having strong theoretical predictions. So we developed the theory beforehand. This will guide your data analysis and prevent finding a fishy, pun intended, combination where your hypothesis is right. Another way that we did this is we focused on model comparisons. So statistics in general, I think I've said this several times, isn't very good at telling which model is right, but is very good at telling you which of two models is better. And then cross-validate. So whatever model you fit, make sure you fit in a new independent sample. So by the way, it's been implicit throughout all this, and actually the last several weeks, that just about everything that we're doing when we're talking about model comparisons and model buildings and those sorts of things, we are in, at best, rough CDA mode, and at worst we are in EDA mode, because we don't have a lot of we haven't fit these models before. This is a model calibration sort of thing. So anytime you do that sort of thing, you are kind of sort of required to do a new independent sample where you don't do any sort of these adjustments and you just run the model as is. Make sense? So yeah. Model comparisons for logistic regression. So fortunately, model comparisons are the same in logistic regression as they were in multiple regression and mixed models. But there are some things that we can't compute. We can't compute R-squared, for example. There are some pseudo R-squared measures out there. SPSS reports them by default. They're pretty dumb though. Because remember that R-squared relies on standard deviations for computations. And so when you're talking about a binary variable, the change in R-squared and the standard deviation, I mean, you can compute the standard deviation of a binary variable, that's no problem, but then when you try to map that on to change and explain variance, it just doesn't really make sense anymore. Now, these metrics have kind of sort of overcome some of these limitations. I think the way that they do it is they look at the predicted versus the actual probabilities. I don't know. I don't know what they do. But in my experience, these measures can behave very oddly. I was doing a project once, for example, where I was comparing the R-squared of two models, and the R-squared of model 1 was better. But when you looked at like the AIC and the BIC and the predicted probabilities, which we'll talk about in a minute, model 2 was actually better. So it didn't even map onto what the other metrics were telling me. So I don't know. I have little faith in these pseudo R-squared measures. But what we can do is we can use the ANOVA function as before, kind of, sort of. We can use the AIC, the BIC, and the Bayes factor. And we could also compare the actual predictions. And fortunately for you, I've wrapped this all into a single function. And unfortunately, this was necessary because you remember how I told you, I don't know, a couple weeks ago, that sometimes R is a little uppity. And if there is no agreed upon way to compute a p-value or a way to compute an effect size or something like that, they just don't report it. Well, this is one of those situations where R is a little uppity. And so if you do the ANOVA function with two different logistic models, it pitches a fit, doesn't give you a p-value, which we're not terribly offended because p-values are meh anyway. But anyway, I've created a function that does all this for you, and it, boy, my video camera likes to just stop recording on occasion. So luckily, I caught it right when it happened. So there is a model.comparison function in the Pfeiffer package. Wahoo! So you use it just like you would with the ANOVA function, where you've got two models, and then you just do model.comparison. and then put in the two models in there, and it will give you a bunch of things. So it will return the AIC of the two models, the BIC, the Bayes factor, and a p-value. And if you look at that, all metrics favor the null model, because remember, a smaller AIC, oh, I said null, I meant to say the full model. So the AIC, the smaller number, belongs to the full model. The BIC, the smaller number, is the full model. The Bayes factor is 2,515. So that tells you, according to the Bayes factor, the full model is 2,515 times more likely than the reduced model, though take that with a grain of salt because it's only an approximation to the Bayes factor. And then the p-value is super small. And remember, when the p-value is small, when we're doing a model comparison, we favor the bigger model, or the full model, in this case, the one that has gender in addition to attention and safety. And so all those metrics agree that the full model is better. Now when we get down into the predictions, so what you can do is logistic regression will output actual predictions. So it's going to say, I predict that you belong to group 1, or you belong to, or I predict that you belong to the injured group versus the not injured group. And so what you can do is you can compare the predictions from logistic regression to the scores that people actually obtained, and that's where the second grouping of metrics come up. So accuracy is, all right, out of all the predictions that you made, how often are you right? And if you look at the difference between them, there's only a 0.2% difference between the full and the reduced model. Sensitivity, we got sensitivity there, we got specificity there, we've got positive predictive value, negative predictive value. If you want to figure out what those mean, look it up online. I can never remember off the top of my head anyway. But what's important here is that across the board, the differences in predictions are very, very small. So even though the model comparisons suggest that AIC, BIC, Bayes factor, and p-value, they all favor the full model, well, the predictions actually aren't that different. So I suspect that the reason why all these favor the full model, despite it being such a minuscule change in prediction, is because the sample size is so big. Because I believe, if I remember right, AIC and BIC use sample size in their computation. P-value for sure does. Well, yeah, because you got a likelihood ratio. Anyway, yeah. So all these are going to use the p-value, the sample size in the computation. So even though it's such a minuscule change in actual predicted values, because it's a large sample size, the functions are concluding that, yeah, this is actually meaningful. Or this is a real difference. It isn't just noise, if that makes sense. But again, the difference in predictions is so tiny. Nothing to write home about, people. Predictions are nearly identical. So in summary, we can visualize logistic regression with a sigmoidal curve, or what was the term that I said earlier? The ogive curve. This can easily be done with Flexplot functions. Predictions can be compared using a Ghostline. But now we have to worry about the, and now we don't have to worry about the assumptions, which is very, very cool. Okay, linear regression makes lots of assumptions. Logistic regression doesn't. The only assumption it really makes is that the outcome is binary. We can also compute estimates with logistic regression. Odds ratios, not intuitive. Standardized odds ratios, a little bit better. And then actual predictions at plus or minus 1 standard deviation. That is quite a bit better. And we could also compare models with logistic regression, so that gets back into our model building strategy, where we can use the AIC, the BIC, the Bayes factor, and the p-value, and we could also use the actual predictions for sensitivity, specificity, blah 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 blah. And those are the objectives. Now, one other thing that I wanted to say, some of you might be thinking, okay, I should have said this a whole lot earlier. So here we are looking at, I said these are intuitive metrics to show you how the differences compare in terms of the actual predicted values. Now, one thing you could do is you could actually go back here and look at the predictions, if that makes sense. You don't need that function to tell you what the predictions are when the line is right there. So you could look at whatever 1 standard deviation above the mean is for attention and 1 standard deviation below, and then just compare the predictions that way, just visually. But the difficulty with doing that is that requires basically a compass and a level, because you have to figure out exactly where the line intersects with X and Y to figure out the exact prediction and the exact prediction over here. That's one of the weaknesses of graphics, is they're not very good at giving you precise values. I mean, they do give you precise values, but we as humans aren't good at figuring out what those precise values are. And so that's why we do this right here, because it's hard to figure out what the exact value is on logistic regression. So with that, woo, well, you lost me. Here were the objectives. Be sure to review them on your own. I'm not going to review them because this video is already really long. Be sure to thank our guest, whoever left. He was an excellent storyteller for the 2 minutes he was in the spotlight. So, ladies and gentlemen, thank you for tuning in with Logistic Regression. Be sure to put whatever questions you have in the comments below. If you're not one of my students, if you are, put it there anyway. I deserve a comment, y'all. Come on now. Otherwise, reserve them for class. It has been a pleasure. We'll see you next time.